10.2, a dilated circle. The image shows two circles. The second circle is a dilation of the first circle using a scale factor of 3. Okay, so we've talked about dilation before in terms of triangles, quadrilaterals, other polygons like that. We know that when you dilate something that the two shapes are similar. We haven't really talked about dilations in reference to circles, so we're going to sort of experiment here and see exactly what happens when you dilate circles. Okay, so for each part of the dilated image, determine the factor by which it's changed when compared to the corresponding part of the original circle. So they want us to find the area, central angle, radius, length of the arc defined by the sector, and ratio of circumference to diameter. So a lot of different information. And we don't know anything about these circles besides the fact that we've got some scale factor of ×3 bringing us from one circle to the other. So the first thing I'm going to look at between these two circles is if they have any similarities. And I can see right off the bat that this central angle here is a right angle, right? Because it's got that box. So I know that that central angle is 90 in both of these circles. So if I'm going from 90 degrees to 90 degrees, what did I multiply my original angle by? Well, if I got the same number, I just multiplied it by 1. So my central angle of the sector is going to be multiplied by 1. It stays the same. Which is interesting because if you remember dilating triangles, other quadrilaterals, the angles in a shape do not change when you dilate it. They remain the same. So the same can be said about the central angle. In a circle, when it's dilated, it is not affected by the dilation. Okay, now we're going to get into some lengths, not measurements of angles. So in order to do that, I want to really get a good idea of what they mean when they say ×3. So I've noticed that, this radius is obviously smaller than this one. So I want to find the exact relationship between those two, so I'm going to use my compass. So I'm going to set it to that first radius, and then see how many times I can fit that first radius in this larger one. So there's 1, there's 2, and I can see it fits perfectly 3 times in this radius. So I know that if this radius had length r, this would be r, 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 or 3r. So we can say that the radius has been multiplied by a scale factor of 3, which is going to be very helpful now in calculating the rest of the information, because all of those formulas are very dependent on radius. Okay, let's do the area of the sector. So if you remember our formula for area of sector, it is area equals theta over 360 times pi r squared, right? Just the fraction of the central angle multiplied by the normal area formula. So let's do that 2 different times for our 2 different areas. Okay, so for both of them, the central angle will be 90. So look at 90 over 360, 90 over 360. Then we're going to both multiply by pi. All right, pi is a constant, that's not going to change. What is going to change is the radius. So for the first one, we've just got r squared. For the second one, we've got 3r squared. And I just made a common mistake, so I'm actually glad I made that mistake. All right, what did I just do incorrectly when I'm calculating the area of the sector here? So hopefully you noticed that I really should have put this exponent outside of these parentheses like that, because I want to square the entire radius, not just the variable, right? This entire radius is 3r. So 3r times 3r is going to be equal to 9r squared. So if you notice the difference between these two formulas, hopefully you can see that the only difference is this is being multiplied by 9 and this is not. So if I wanted to find a ratio or the factor between these two areas, what I would do mathematically is I would put the larger ratio or larger area over the smaller one. some of you probably can already see this, and you know, this is just what's going on in your head. So whatever you do, if you're got terms in the top, they're all being multiplied, and terms on the bottom of a fraction that are all being multiplied. Anything that's in common between the numerator and denominator, we can just cancel out. So 90 over 360 we can cancel out, pi we can cancel out, and r squared we can cancel out, and all we're going to be left with is 9 over 1, or just 9. So the area of the sector has a scale factor times 9, which hopefully you also recognize is just the same as saying times 3 squared. Right? Because that scale factor of 3 is really what's creating that scale factor of 9. When we talk about a single length or a one-dimensional length like the radius, right, we're just multiplying 3 once. When we're talking about a two-dimensional measurement like area, you can see we've multiplied by 3 twice, squaring it. That's why we talk about units in area are units squared. One-dimensional lengths like radius or circumference would just be in units, not units squared. Okay, so let's experiment a little bit more with this. The length of the arc defined by the sector. So we can compare those two formulas pretty quickly as well. All right, that formula is L equals theta over 360 times 2 times pi times r. So that's literally going to be my formula. Actually, I'm sorry. I got to plug in the central angle too. So for my smaller circle, we'll have 90 over 360 times 2 times pi times r. For my larger circle, we'll have 90 over 360, central angle hasn't changed, times 2 times pi. Now instead of r, I'm going to substitute in a 3r. So I could go ahead and make that fraction again and cancel out whatever's in common, but you can sort of see it here. These are going to cancel out, 2's are going to cancel out, pi's are going to cancel out, and that r is going to cancel out, and all that's left is 3. And that makes sense, because circumference, like I mentioned, is a one-dimensional measurement, so it's going to be affected by the scale factor just straight up, times 3. Right, the ratio of the circle's circumference to its diameter. So that's something we've never talked about before. That's pretty interesting. So let's look at that. So the ratio of the circle's circumference to its diameter. So let's make a table. Let's make small. Let's make large. Then let's have the circumference here. And let's have the diameter, because those are going to be different for both of these circles. Let's see if the ratios end up being the same. So for the small one, my circumference is just going to be 2 times pi times r. Right? It's literally the exact formula for circumference, because our variable for radius, we're just using r. For the large one, it's going to be 2 times pi, and instead of r, we're using 3r. So more simply, I can say this is 6 times pi times r. I combined the 2 times 3 because they're like terms. All right, now the diameter. That's pretty easy, right? I just double the radius. So if that's r, my diameter is 2r. The large one, if my radius is 3r, my diameter is 6r. So now we're creating a ratio between the circumference to the diameter. That's really just a fancy word in this case for a fraction. So for small, you've got 2 times pi times r over 2r. Cancel out the 2's, cancel out the r's, and we're left with pi. Let's try for the large. I have a feeling we're going to get the same result. 6 times pi times r over 6 times r. Cancel out the 6's, cancel out the r's, and we're left with pi. So my ratio for 5 is going to be pi. So that's interesting to see that no matter what size of a circle we have, the ratio between circumference and diameter will always be the same. All right, that is all for 10.2.